Welcome to The Explainer. Today, we're diving headfirst into a thought experiment that really challenges the way we think about reality itself. And believe it or not, it all kicks off with this super strange behavior of a single particle of light. Okay, so before we get into the weeds, we've got to be crystal clear on our main clue here, what a paradox actually is. It's not some impossible, unsolvable riddle. It's much more like a little flag the universe is waving at us, telling us, hey, you need to look deeper here. Your current understanding is missing a pretty big piece of the puzzle. And this idea? It's absolutely central to our whole explainer. See, even our most rock-solid theories, like Einstein's general relativity, they don't just describe the universe out there. They also, kind of sneakily, highlight our own built-in limitation. We are always observing things from a very specific, single point of view. In fact, all of science basically depends on separating the observer from the thing being observed. So how does that one limitation create a massive wrinkle in space-time? Well, this whole mystery gets started with two fundamental rules from general relativity. And these aren't just guesses, these are principles that have been tested and proven to be true time and time again. Right. So, before we can even step into the paradox, we need to understand the rules of this cosmic game. And again, these are not just abstract theories. We're talking about two confirmed real-world effects that gravity has on light and on time itself. Now, what's so fascinating here is that you're really looking at two sides of the very same coin. On one hand, gravity can literally change a photon's energy, but on the other, it also changes how fast a clock ticks. Both are just perfect examples of how gravity fundamentally warps our measurements of reality. Okay, first up, redshift. I want you to imagine throwing a ball straight up in the air. As it fights against gravity, it slows down, right? Well, it's pretty much the same thing for a photon. If you send one from Earth out into space, it loses energy as it climbs out of Earth's gravity well, and we can measure that energy loss as a drop in its frequency. It shifts toward the red end of the light spectrum. This isn't just an idea, it's a measured fact. And second, we've got time dilation. Now, this one might sound like something straight out of science fiction, but I promise you, it's an everyday reality. We have physically measured that atomic clocks literally run faster in orbit than they do down here on Earth's surface. In fact, the GPS on your phone only works because we are constantly accounting for the fact that time itself is ticking away at a different rate for those satellites than it is for us. Wild, right? All right, so with those two cosmic rules firmly in place, our little experiment can finally begin. I want you to imagine we're in a lab, right here on Earth, and we have three perfectly identical photons. Same energy, same frequency, they are exact twins. So here's the plan. We're going to keep one of those photons, photon 1, right here on Earth. That's our control group. The other two, photons 2 and 3, we're going to send out into space on the exact same trip. And then we make a really important decision. We just decide that photon 3 is now our clock. Its new job is to measure its twin, photon 2. Okay, so let's just pause for a second and think this through. We know from rule number 2 that clocks tick faster where gravity is weaker, right? And because a photon oscillates at a specific frequency, you can totally treat it like a tiny, tiny clock. So what happens to our new clock, photon 3, once it gets up into space? Exactly. According to time dilation, its little clock should start ticking faster. And a faster tick means a higher frequency. For light, a higher frequency means it shifts toward the blue end of the spectrum. So it gets blue shifted. It actually gains energy. Now here's the really crucial point. Photon 2 and photon 3 are identical, and they took the exact same journey. So if photon 3 gets blue shifted, then it stands to reason that photon 2 must also experience the exact same blue shift. From the perspective of any outside observer, like us, they are still identical twins, no difference at all. But now for the twist. We've just established what an outside observer would see. But what happens when our newly designated clock, photon 3, actually does its job and takes a measurement of its twin? Let's really try to put ourselves in the, well, not shoes, but in the perspective of photon 3. It's now way up in space, and its own internal clock is ticking much, much faster than it was on Earth. For photon 3, time itself has literally sped up. So, from this sped up point of view, as photon 2 zips by, photon 3 measures it.
But think about it. Because Photon 3's own seconds are flying by so quickly, it ends up counting way more of its own ticks during a single oscillation of Photon 2. And because of that, it comes to a startling conclusion. Its twin, Photon 2, has a lower frequency. From its perspective, it sees a redshift.
And boom, this right here perfectly illustrates the paradox. We have two completely valid perspectives, both using the same exact rules of physics, and they lead to two totally opposite conclusions about the very same photon. One perspective says they're identical, the other says they're different. How can that be?
I mean, this is the absolute core of the mystery. Nothing physically different happened to Photon 3. It didn't change its path or its nature. The only thing that changed was a human decision, our act of labeling it a measurement device. How on earth can a simple change in our perspective, our intention to measure something, create two completely different realities for Photon 2?
So, what's the solution? How do we resolve this? Well, the source material for this explainer suggests that maybe the problem isn't with the photons, and it's not even with Einstein's theories. Maybe the problem is with one of our most fundamental assumptions, that the observer and the observed are truly separate things to begin with.
So on the left, you've got the standard way physics works. The thing doing the measuring is separate from the thing being measured. Simple enough. But the proposed solution on the right, it challenges that entire idea. It suggests that the separation we assume is just an illusion, and that both the clock and the photon are really just different ripples in a single, deeply interconnected reality.
So this theory argues that what's fundamentally real is that both photons do get blue shifted, and they do stay identical. The paradox only rears its head when we try to impose our human, perspective-bound measurement onto the situation. That act of measuring creates a relative illusion of difference, that redshift, but it doesn't change the underlying reality that, deep down, the photons are still the same. So if there's one thing to take away from all this, it's that the contradiction might not exist out there in reality itself. Reality is probably perfectly consistent. The contradiction could just be a side effect of the scientific method, which forces us to draw a neat little line between the observer and the observed, a line that maybe doesn't actually exist in the real world. And that kind of leaves us with a final big thought to chew on. Maybe the universe isn't just the sum total of all the data points our instruments can give us. Perhaps reality is a much more unified, interconnected, and fundamentally stranger fabric than our perspective-based measurements could ever hope to fully describe.